Hey everybody, this is Larry. This is day 14th of the Leetcode Day Challenge. Do we have a new weekly problem? No, that's tomorrow. Okay. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Today I played pickleball, is it? For the first time, and I hurt myself. This is what happens when you're old and you play an old person's sport and you still hurt yourself. I mean, I've had a bad hamstring for a little bit, so I'm going to try to see how much I can do with this one, and then going to ice it a lot and call it an early night. All right, today's problem is 332 Reconstruct Itinerary. All right, so you're from and to, all the tickets belong depart from JFK. Hey, that's me, maybe. It must start with JFK, and the smallest lexicographical order when return is a single string. Okay, fine. What am I doing? Oh, so every ticket has to be used. Is that it? Can you always have an answer? Okay. So then, in this case, it's a very it's a directed graph, and it is what you call it, Euclidean path, right? Yeah, it's not a cycle because we don't always stop at JFK. So yeah, so it's an Euclidean path. You have to kind of look at each edge once, and in this case, just to be clear, actually I don't know if that's true. Let me double check. I mean, I think it is, unless I'm misreading it. You can go between two cities multiple times. So yeah, and yeah, and so then now. I do wonder if there's a straightforward, right, but let me type that up real quick. So directed Euclidean path is kind of what we want, right? We want to look at each edge once. And the way to kind of think about it is there is yeah, I mean, there was an algorithm. I forget the name off my head. I think it's like it's named after some dude, but basically the idea is to kind of use depth first search. Um, I think it's called like the hose something algorithm, the Hosinger, Horsinger. Okay, fine. So you know you have this algorithm, but at the end of the day, it is going to be yeah, the idea is kind of using depth first search by using stacks, and basically you want to. This is a kind of advanced thing. I don't. Let me finish explaining, and then let me take a look again to see if there's any like more easier way to do it. It is going to be linear, but maybe we don't need linear. But the idea behind it in this algorithm is just that when you kind of see a cycle, then now you can kind of take out that cycle and then kind of combine all these cycles in a way so that when you combine these cycles in a way, then you get one path, right? Because when you kind of visualize the cycles, you can and I don't know if I should draw it, but you can kind of visualize the cycles and they kind of connect in some way. You can kind of think about the maybe another way to think about it is that when you have these nodes, you can kind of collapse these paths, and of course once you collapse them, then now you have you know, you have these cycles, and then you can kind of just, it doesn't matter where you go because you can always go back, which is the thing about a cycle, right? And because of that, if you didn't take the same way in or take the same way out, you have, you know, another way in. You have given a cycle, given a node on a cycle that, you know, if you have multiple cycles, the number of out paths is always going to be the number of in paths, right? So I mean that's kind of, you know, like if you're in two cycles, then you have two paths going out and you have two paths going in. That's at the very least, because that's, you know, that's how cycles work. That's kind of the general idea. That's gonna be v plus e, and yeah, I mean it's fine. Of course, I mean of course it's gonna be fast enough, but it's maybe too fast. Yeah, just because, if n is equal to 300, or this is e actually, n is maybe less than 300, but, or probably is less than, I guess it could be more than 300. It could be like 200 times 2 or something like this, though it wouldn't be connected, so maybe that's a little bit odd. But it'll be like about 300, say. That's the max anyway. So then we probably could do some n square stuff. I actually don't remember. Let me see if I can prove one off my head. But I think the idea is that you kind of take the path. I think the lazy way to do it, or like the way that I think could be done, is just, take a node, right? So we start at JFK, right? And then now we take the quote unquote smallest, and by smallest I mean the lexicographically smallest, because that's one of the constraints, right? Take the smallest node that still leaves us a way to for an Euclidean path to exist. So that's basically the idea. And if you do it this way, it's going to be n squared. But n is 300, so it's going to be good enough. And in this case, n maybe v plus e, and also 300 is going to be good enough square. Because you could check this in pretty straightforward. Can you? Well, I'm pretty sure you can. I have to think about it a little bit, because I usually do this with, or this comes up for undirected graphs, but I have to think about how to kind of check this for directed graphs. What does it mean to have a path, right? It means that so it has to be connected. The entire, you have to be able to reach every node. So what makes, so. And I'm just to be clear, like, I'm not reading off anything. I'm just trying to think about it from a first principle thing, right? And of course, I don't know. I read this debate recently on Discord. People talk about memorization and stuff like this, and yeah, memorization would make it easier, but the thing is, or faster anyway. But you don't need it, right? Like, when you learn, you can figure out these things just by some observations, right? And in this case, yeah, obviously it has to be connected. If it's not connected, there's no Euclidean path for obvious reason. And then every node, other than one node, has to have the same in degree as your out degree, right? Except for 2, I suppose. And 2 being like one node in the big. It has to be the node that we're starting from, which would have to be the smallest node, and then one. So yeah, in degree, you go to out degree. So 1 minus 1. Yeah. Wait. So for the current node, you want to have out degree plus 1, right? Or maybe I said it wrong. So you want to have one more out degree than in degree, because this is the one that's going out, right? So then you come in. So yeah. This is for starting node or current node maybe, and then in degree you go out degree plus 1 is some random last node. I think these are good enough. Definitely that's good enough for undirected, but to be honest, I think that's still true for directed. And for undirected, the definition of in degree and out degree is a little bit trickier, right? Because then in that case, it's not even just in degree and out degree. It is just the number of degrees, right? And then in that case, that's right. The number of degrees have to be even, except for 2 of them, the beginning and the end, which they have to be odd. Okay, so I think now we, definitely if you're interested in this algorithm, and I think it's still based off the same idea of just like connecting cycles and circles and so forth. And you could kind of do it with a depth first search or stack or something like this. and this is going to be linear time. But I think we kind of came up with an n square thing, which for this particular problem is good enough, and probably what they're asking for anyway. Though, I mean, I think for an interview, the n square is probably good enough, in the sense that it actually requires some kind of thinking. I mean, I hesitate to generalize because who knows these days, right? I think I talk about this sometimes with respect to, like, to be frank, a lot of interviewers are not good either with what they're looking for, and if they just kind of copy this problem off like a problem bank or something like this, and like, oh yeah, the optimal is obviously linear, but without really giving a thought about it, then they'll be like, oh yeah, then they'll judge people whether they know this random algorithm. And to be honest, like I said, I don't know. I mean, I could probably come up with it and put. I know the ideas because it's been but I it would take me forever to kind of actually do it, even on an interview, right? Like, I mean, even for me on explaining it, it's kind of a little bit hand wavy, and I understand that because but if you don't get a crappy interviewer who don't know what they're doing, or maybe they know what they're doing and they're inflicting pain, then maybe you need linear time. But I think like the nonlinear one, the quadratic one, is a little bit more interesting for me, and so I'm gonna just type it that way. I mean, otherwise it's just you plug and play the algorithm. It's not really, I don't know, like what do you actually learn? I mean, and then there's the other thing, right? As an interviewer, the thing that I look for is just problem solving skill, right? That's why that's the main idea here, and not someone's memorization skill. Or at least not during that component, right? There are other, like, if for whatever reason, if you're in a job that needs this to know this particular algorithm, then fine, but you would do it during like a trivia problem or a trivia portion of the interview, and not the problem solving part of the interview, which is what I'm more interested in kind of communicating. I think that's all I have for the chat, so let's kind of get started, right? So, first of all, let's just do out degree. Let's have a collections.counter in degrees, also collections.counter, right? And then now we have for was it source and sync, source and sync, or just UV. Let me just use more standard graph terms. So out degrees of u in degrees of v right? And then now we have answer is equal to JFK, just because that is the hard-coded thing, right? And then now what? Yeah. What do I want to do? Just thinking about what's the best way to represent this. I mean, I think it's fine. I'm just gonna be a little bit lazy. I think I need to construct an edge list. I think that's what I need to do, actually. Yeah. And here, keeping in mind some of the reasons why I do it this way instead of the Hauser algorithm, I'm probably saying that well, is that there is an additional constraint of the smaller lexicographical order, which, to be honest, I kind of get the idea about this, but it would take, like, I don't know that it would be easy to kind of do the lexicographical order, where here, the way that we do it is just that we choose the quote-unquote the smallest node, so we know that that's going to be the best lexicographical order as long as we have a valid solution, because it only matters, it's like the most significant bit thing, right? Like, only your most significant bit matters. Your least significant bit matters as a tiebreaker. So if you're greedy every step of the way, assuming that you're still able to get an Orleanian path, then you should be good. Of course, and here that is part of the constraints, which is why we are good. Oh yeah. And then E of U dot append V, right? All right. So then now, let's just say M for edges is equal to length of tickets. Yeah, I mean, I think there are a couple of ways you could do it, but I'm just going to do a very standard used thing. Right? And I mean, there's only 300 tickets, so not going to worry about it. And we iterate 300 times for whatever, so yeah. You go and the last city, and then now, what do we want to do, right? Actually, yeah, I think actually what I want is actually just sort this anyway, so that so lexicographically, so then we don't have to do a loop. I mean, we still will have to do a loop, so I think in the worst case it doesn't change anything, but I think it allows us to do like some early termination thing that makes it slightly easier to read. Maybe, I don't know if that's true. So yeah, so for key in ye.keys, ye.key dot sort, right? And then now we start at the current, and then we just for next in ye.current, and then now if good of from current to next, then answer.append next, and then we break out this loop, right? Otherwise, this should never happen, but I don't know, maybe there is some bad coding, so then I want to put an assertion there, and then at the end we just return answer. I think that should be good. Of course, we have to write this good function, which is easier said than done, but maybe just previous current, right? Or candidate, maybe. We just have to implement this thing, right? So let me think about this for a second. I mean, the other stuff is easy to do. The connected part, we want to do a depth first search, but we also want to disconnect the stuff that we've already done, right? So I think we have to be a little bit careful about it. And we don't, oh, I guess that's what the use is for. But I don't tie this to anything, so it's a little bit awkward. I mean, there are two ways to do it. Maybe there's one way, which is this, and then the other way, which is just removing this, which means that we want to remove in better than O of n times. Though I guess O of n times wouldn't that matter because we only remove it once. But yeah, let's just. We'll probably have to. There's this. We probably have to think about this a little bit if we want to optimize. But I think something like this is probably okay. Let me just return true real quick. I don't know if this runs into like the iteration concurrency or whatever error. Okay, it doesn't seem like it. I mean, I think it might be if we didn't have to break, because I think we modified. Okay, well maybe that's a thing. Because removing things in the middle of an iteration is a little bit sketch. I'll keep it here for now, but hopefully the idea makes sense in any case. Yeah, and it actually returns some stuff though. Actually, it's just very lucky that this happens to me. Maybe there's only like one way of doing it, that's why. But it gets a little bit more complicated, or at the very least, you have to deal with tie breaking when there are more than one ways of tying things together. And this one, there's no. Yeah, that's just so lucky. It feels a little bit silly, but okay. So then now we want to calculate if we are at candidate. Is the graph still connected, right? So yeah, the remaining graph is still connected. Man, this is a little. I mean, the way I'm writing is kind of yucky, but I guess it's just. Oh, and here, I think I have to write something like in degrees of Next, we decrement from 1. Out degrees of current, we also subtract 1. Yeah, because we remove the edge, right? Just run it real quick. Okay. So then now, I guess it's just for keys in key in degrees of keys. Just like things that we have to consider, right? So nodes is equal to just a set, right? So then nodes dot add key, I guess this is just actually this plus out degrees of keys. Oh no. Reason why I can't do it, and that's why I wrote it out, is that I have to make sure that this is greater than 0. I guess you could kind of write it. You can still write in one loop, I suppose, one statement, but I'll just write it out since I don't know. I've been making a lot of silly mistakes lately, so let's, I don't know, just kind of do the, not trying to be too clever here. Okay, right? So then now these are the nodes that we care about. I think it's a little bit tricky because now we have to write something like degrees of current in degrees of candidate, almost like a like like a depth first search state thing, right? Because we want to make sure that like we're treating it as if now we use this node from current to candidate, or this ticket from current to candidate, and then now from candidate is there a way to kind of reach every node, right? So that's basically the idea. So then in that case, I have to do this thing too. So yeah, E of current dot remove candidate, and then here E that current dot append candidate. So now it becomes this is a little bit yucky actually, because then now this may not be sorted anymore, you know? I mean, definitely not if you're going to remove and then put it at the end. And this is probably in the beginning, the way that we do it. This is such a mess. How did I do it last time? I probably just grind, but I mean, okay, I kind of try to avoid it, but I think just using sorted list would solve this. What is it from sorted containers? All right, and then now I can just do an add or insert, is it? Oh no, add is fine. We don't need to sort anymore. And then here, I think this is fine maybe. Well, let's just run it real quick. Sorted, okay, fine. Keys, yep. Yeah, I knew that. I just didn't know where I have it. I might have another one. Okay. Yeah, because we don't return anything. Okay. Right. Okay, so this kind of sets everything up. Right, and then now is the graph connected from candidate, right? And maybe even before we do this, we'll do the other checks first, because the other checks are much cheaper. So these things, right? So yeah, so maybe how do I want to write it, right? So for key in degrees dot keys, if I want to make sure that both things have the same keys. So I'm just going to write something like this to kind of to make sure that they exist, right? So that now we can, instead of write it this weird way, we can actually just put in the same loop, right? And then here, and you could actually probably just like put it on an actual list. I'm kind of taking a long time here. I'm also very tired. Okay, what am I doing? So for key and keys, okay, so if in degree sub key is equal to out degree sub key, then we're good, right? So if it's not, then it has to be one of these two cases, right? So if key is equal to current and in degrees of key plus 1 is equal to out degrees of key, then maybe I sort of like start found is equal to false and found is equal to false, right? Okay, so if this is true, then sound found is equal to true. Otherwise, then if in degrees of key plus is equal to out degrees of key plus 1, then n found is equal to true. Of course, we have to kind of if start found, for whatever reason, I don't think this can be possible because of the key is equal to current, but if start found, then we return false, but we have to kind of fix the states. So we might have to kind of write a wrapper about this so that's a little bit easier to do. Right, so right, so maybe we do something like or maybe the other way. So yeah, if degrees okay, right? Or if this is not, degrees is not okay, then we want to return false, kind of, but we have to do the other things first, right? So and maybe I should just write decorator, but that's just confusing, right? If it's not okay, we want to return false. But maybe we just do, if returns is okay, then we do something, right? And then we return false. Yeah, this is a little bit yucky. It's a lot yucky. Okay. Let's finish this part first. Yeah, and then also, yeah, if n found, then we have two of these for whatever reason, and then we return false. Otherwise, if it's equal, it's fine. Otherwise, if it's not the same, then we return false. Otherwise, we return true, I think. Hopefully this is right. This is where you would maybe have a unit test for just this. I mean, not quite, just because we can't deal with weird states here. So I'm already kind of violating that a bit. But I do rely on a lot of global states. Why is this so long? Okay. And now let's say the degrees part is correct. This may be one of those days where I have a lot of submissions. Then now we can do the connecting part. So now, okay, so right? These are the things that we care about. And then now we want to see if we can visit all of them. So a new current, right? Current and then parent, and then for v and y of current, I'm trying to think whether we need this to be connected or strongly connected. I think connected is probably fine, given all the other conditions. But maybe I'm wrong on this one. I don't know, to be honest. We'll play around with it. I mean, if it's wrong, it's wrong. Okay. Yeah, if we is not equal to parent. Actually, I guess it doesn't matter, because in theory, can go back and forth and back and forth. So as long as we have to. Oh no, I mean, that part is true, but I think for connectivity, we don't need it. So yeah, okay, fine. Well, I don't know if I'm convinced, but yeah. So that, but also, and we haven't seen it yet, I guess. Right, and then now we just, if seen is equal to nodes, then we're good. Maybe I just do an R. R is equal to false, and then true. Because then it does the cleanup. This is so yucky though, not gonna lie. Oof. So what this means is that this is returning false for everything. So that's not great. Do I just do it for, okay, I don't know, it doesn't say. Definitely not great. But, is it this part or, One start, one end. I think there's an additional case where this is wrong, which is if end found is true, but if like if start found and not end found, or I guess technically only one of them. So you could do like an int add or something, but I think that's like less readable. Something like that, but that doesn't change our thing because that makes it even more unlikely. But I want to, where am I getting this wrong? Let's see. Current candidate. Does that even come out with anything before we crash? No. So that means the degrees okay is kind of awkward, for sure. Maybe just here first. Key. Yeah, that doesn't help enough, but I guess we'll just see. Huh, that doesn't, not even that. So what is going on? It's not here. Alright, let's just see that we're actually getting here at least. Okay. So the first one is JFK to Munich. Right, and here it is going to remove these nodes or whatever. So then now we're at Munich. And for each degree, where is this not the case? I'll just print everything out real quick. So yeah, okay, Munich. Yeah. So Munich is the start. We start as found. Okay. In degree. Actually, that's. Why do I have to in 2 degree for in degree? Did I mess up? Well, that's just wrong. So. Huh. Did I add one somewhere by accident? Oh, huh. Why do I do this? This is not. Why would you add one? That was just really bad. Okay. I don't know why. Okay. All right. At least this now is sensible. Out degree is 1, in degree is 0, and then I guess that asserts false versus returns false for whatever reason. But that was pretty bad. Okay. So then now, what is it doing? My watch is always telling me to stand up, and I'm always telling it I'm lazy. Okay. So the degrees thing, something failed. So if key is you go, so okay, in degrees, right? In degrees, so no, this is good. This is what we want. And then start is equal to true, and then we go on, right? So why is that returning false already? Key is equal to current. Right, what is current? Maybe current is wrong. Current doesn't make sense. There's no current. I don't pass it in, so that's why this is weird. And like current is the last current, possibly, so it's not consistent. Yeah, I meant candidate. That is one thing that's kind of sometimes a little bit sketchy about Python, is that it's very easy to make mistakes like this. Okay, so then now it's still giving an error. Munich, that thing passes. SJC 1 0. Oh yeah, that's the outbound, right? So in degrees is equal, that's fine, right? And found. It should be here, right? But if it's not, then something's a little bit awkward. Yeah, so that founds it here. And then the next, why is there only two things? That's not true. I mean, it finds the SJC, so it's here. So then it should go to the next loop, right? Oh, because they're all equal the same, so that's why it's not printing. Okay, that I could understand. So then why is it, Do I have like a bad conditional? Maybe. Kind of. I mean, I have bad typing, so why not bad conditional? True, true. Okay, so if this is true, true and false, or false and true. So yeah, so this should return true then, right? Why is that giving me an insertion error? So it is giving me here, and then still giving me an insertion error. Let me print out what this means. Is this after we do an iteration? I guess no. I thought that returns good. Okay, I guess this thing now, I wouldn't say it's fixed, but it's doing maybe more closer than we expected. So that means that this DFS thing is kind of being bad. So okay, so let's see. Print scene and notes. Okay. Scene is nothing. Oh, I didn't call the DFS, did I? So so candidate, and I think it doesn't matter what the pound shouldn't be used here. So okay, but both of these things are kind of wrong. Why is note only these two? Yeah, why is it only those two? Man, I don't know how to code today. Alright, yeah, so it should have a bunch of stuff. And in fact it does, I guess. Right? Okay, so it does, and then it returns true, right? So does it not return true after this? Tell me why. Where is this print from? This print is from here, right? So then why is it, what? Oh, and then now it goes to, yeah, okay, fine. Let's add a thing here for do, and then now it goes from JFK, and then next iteration it goes to MUC. Is it Munich? I actually don't know what, I'm curious. I just keep saying Munich. I guess it is Munich. Okay, so I'm not making things up. I've been to that airport, but I've been to a lot of airports. Okay, so then now that means that this is the first loop. The first loop actually turned out okay. Goes to Munich, and then this is when things went awry. Why is that? Tell me why. Okay, so I mean it does know to go to LHR, right? I'm debugging this so badly. Okay. So Munich LHR, okay, but it's giving a 4 somewhere. That's a little bit sad, right? Oops. Okay, so that means that degrees part is wrong, right? Yeah. Did I know this? I don't know. So LHR, okay. So why is this returning? Is it here? Nope. So it terminated a little bit earlier. Let's kind of look at both, I suppose. I can take a shower and sleep. Maybe I should do these in the morning. I don't know anymore. Okay. What is the here for again? Oh, this one. Just the first call. Okay. Ooh. Do I? Oh, these things we have to add back in. Okay. I am a silly boy. I don't know why I was so inconsistent. There's so many silly mistakes, to be honest. But yeah, one look. Oh, so we're good. Kind of. I might have. Maybe this is M minus 1. 1, 2, 3, 4. I don't know. Now we're in SFO, so SFO we have to go SJC. But maybe there's something with the emptiness. Okay, let's take a look. SFO to SJC, degrees okay, okay. And then now we have to do that first search. The number of nodes are actually there are no nodes, but we've seen SJC. So that's not right. Okay, so we just have to fix this, I guess. Let me also, I was going to say, let me look at problem 2. Or not example 2, but how do I fix this? I mean, this seems, we're pretty much done. Or, well, if it's correct, we're pretty much done, but we have to figure out how to do our scene thing. I guess we could do something like this instead, but that just seems a little bit weird, to be honest. Right. Yeah, and now this terminates earlier. Because in essential, we're just skipping the first thing, but then the nodes is a little bit awkward. Is that on? It should be just SJC, is it? Because it's assuming that. Okay, fine. Maybe I can just do nodes that add candidate, because that's the thing that we're always going to visit. And it looks okay for these, but then, you know, for the example, it worked okay even on crappy, like when we just return true for some random stuff, right? So I don't know that I put that much stake in it, but let's you know, I guess this one I could leave in because that's a cert anyway, so it should never happen. And if it happens, then, you know, yeah, let's at least add some weird, slightly more weird cases. Okay. Right, something like that. I'm not confident about that one, to be honest. Seems okay though. What's the timing? The timing looks okay too. I mean, this isn't crazy intense, and apparently we have some extra print statements that we probably should get rid of. So that would actually be sad if I could find them. It's right here. Okay, there we go. Is there a bigger case? I'm just going to submit just because I'm lazy, but I'm like not super confident, but I guess we're fine. Yeah, I mean, it's fine. Whew. This was a tough one. Is it a hard? I mean, it's fine. I think I just kind of took my time, to be honest, to kind of go through it step by step. It's a very long step. What did I do last time? I got it. No, I guess the last time I did use what's his name's algorithm? Hauser algorithm. Oh, I think. This is a really weird way of doing it. I think the observation here, which I did not use this time, is I think the thing is that because it will always have at least one answer. I think that this other one is probably a little bit a lot smarter, because they're now just saying, okay, take and the reason of having this is just so that we have it in order, because otherwise you can take anything, and I guess it's impossible to get stuck. Is that true? Is it impossible to get stuck? I thought that there may be a weird case where, I don't know, you go to ABC and then oh, I see. This actually appends at the end, so this will come. So you're kind of, man, I do not know this one. Not gonna lie, I don't. It's been a while, so I might not be strong enough. I mean, this was 3 years ago. I mean, this is just the algorithm, but okay. Yeah, let's go with the complexity really quickly. I mean, I think we kind of laid out what we're trying to do here. So it should be pretty straightforward. This has M loop, so this is all of M iterations, and for each one we do a thing, right? We look at the next node, and for each node we do a linear thing. So yeah. But keep in mind that, and there's some log factor here, so I'm a little bit sloppy with this one. But keeping in mind that for each one, we... is that true? I don't know. I think maybe there is some, like, quirk of the thing. Because I'm trying to think about, like, this case where you have something like JFK, ABC, right? And then maybe... I don't know, JFK, DF. I mean, this is going to work for me, but I don't know how this works for the older example. I think that's the thing that I was trying to do. Let's see. I mean, this should be pretty straightforward here because we're literally doing the n square solution. But if we look at this one, how does this work? I mean, it is just algorithm, but And technically, I don't even need non-local. I think that was when I was just still starting Python 3 because I had Python 2 experience prior. But basically, it's saying if there's an edge, we recursively construct it. Yeah, I don't know. I don't know. Today I'm just tired, but I think hopefully, let's take a look at some solutions. Maybe I'm just being silly. Yeah, I mean, I don't know what's going on here. I mean, this is basically the way that I was doing it, but I don't understand this way. This way is just, I feel like it, I don't know. I might have to watch Larry's older video. But I think this is just what the guy's algorithm, I think. Trying to find the window for, it's fine. Anyway, sorry friends if this kind of left on a cliffhanger. Hopefully this was understandable. This is not the code. I want to show the code that I wrote today. Yeah, let me know what you think. This is the top and this is the end. And you know, this comes up quite a bit, this kind of thing. It's just that for each edge, we are going to, you know, do it. I guess this is always good, maybe. So, I don't know. Anyway, that's all I have for this one. Let me know what you think. And yeah, stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye-bye.